Going live, so I don't have a video on this. So let's see what other problems we can do. So here's the next one. Let's look at our book. Look at example 3 in your book. And we'll write down a couple things off of that. Okay? So example 3, we're going to do that one. I made a program for that.
Good mic. I know with your new computer.
Okay. So can someone help me set up some of the equations for that one? Try to fit them in here. So what are we supposed to do in this problem? Someone want to read it to me?
Which one?
Example 3.
A rectangular page is to contain 24 square inches of print. The margins at the top and bottom of the page are to be 1.5 inches, and the margins on the left and right are to be 1 inch. What will the dimensions of the page be so that the least amount of paper is used?
Okay, so we're supposed to find the dimensions of this paper that accomplish a maximum or accomplish a minimum? They want us to minimize the amount of paper used, right? I think they told us two things. So we're working with like a piece of paper like this that has an area. So for ours, they said a couple things. The margins, are they the same size of margins? What did they say like the top and bottom are supposed to be?
1.5.
The length or the...
So they said 1.5 this way and 1.5 that way, is that right?
Yes.
So it's like 1.5 right here, and 1.5 right here. And what do they call this dimension? They call it X or Y? I think they called it X, didn't they?
Yeah.
From like here to there.
Yep.
That's what they called X. Okay, and then they said these other dimensions, they've got to fix those. They're a little bit thinner, aren't they, at 1? So this is like 1, and this is like 1, and from this edge to this edge right here is going to be unknown, because that's what we're trying to figure out, so that we can not waste as much paper as possible. Okay, so we've got that. What else did they say? They had one other like constraint on the situation, they said. Did they tell us like they needed to have a certain amount of print?
24 square inches.
Okay, so we're going to have two equations on this one. And the last one we had a primary equation only. It was just a distance formula. Yeah? This one I think we've got like two equations. So can somebody help me with one of those equations? I mean, you've got the example in front of you. What are we trying to maximize or minimize again?
The area.
The area. So that's probably the primary equation. You know what I'm saying? So area. What is the area of this thing? Well, you've got a picture of it, so just tell me. Area is always like length times width, right?
Right.
So what's like this length, this dimension?
It's
Y
y plus
times
2.
It's y, which is this much, and then those little extra pieces are 2, so it's y plus 2, right? And then this dimension is going to be
X plus 3.
x plus 3. You guys see that? And there's our primary equation. That's the thing which we're trying to minimize. The only problem with it right now is that we only know single variable calculus. Do you know how to differentiate a multivariable function? You don't, right? This has how many variables in it? It has 2 variables, right? Can you guys see that? X and y. So this function right now is a function of 2 variables, x and y. So somehow we've got to get rid of one of those variables. So that's the purpose of a secondary equation.
Didn't we do multiple 2? Oh, yeah.
We know how to take a derivative implicitly,
No, this isn't implicit.
but this isn't implicit.
It's like 3 variables.
Yeah, we haven't learned anything about how to maximize or minimize implicitly, right? That'd be another thing. But good point, very good point. So somehow can we get rid of one of those x's or y's? And that's where they told us something else that we had to do, right? They told us that we also had to only have or have enough to have.
24 inches.
They wanted exactly 24 inches. So that's the secondary equation. So 24 equals what?
Y times X.
Y times X. Why is that?
Because it's just the area of the paper. So.
That's just the inside area, right? And we call that inside Y by X if you look at our little diagram. Does that make sense? So this has to be satisfied as well, at the same time as that, but that also gives us a way to get rid of one of the variables. So we can say, okay, what did the book choose? They solved for what? They solved for Y.
Yes.
So if you solve for Y, it's 24 over X. You just stick that in there and you'll get rid of one of your variables. So that's the idea. Okay, so then we're going to say A of just X, only depending on one single variable, is going to be, if we stick this in right here, 24 over X plus 2, and then we've got X plus 3. And that's a single variable, so now we can take the derivative and find the minimum that they wanted. Does that make sense? Anyway, pretty powerful stuff. So let's look at the simulation real quick and just see what's happening, and then we'll do the rest of the math. So that's the idea. Let's play with the simulation. Where's my thing? Ah, Austin's got it. Thank you. So you can see your piece of paper here. The margins look like they're fixed, right? When I move this around, are the margins changing? The margins are not changing. The only thing that's changing is the overall dimensions. So you can see that the maximum, or excuse me, the minimum amount of paper used to accomplish this is going to happen about right here somewhere. Can you see that on that curve over there?
Yeah.
That's the amount of area curve over there. So it's going to happen somewhere like this with a nice rectangular sheet. That looks like an 8 by 11 sheet, doesn't it? So why are 8 by 11 sheets what you use most of the time? It's because it accomplishes this kind of thing and wastes the least amount of paper. So kind of simple, but also something you never thought about, I bet. Anyway, let's do the math and figure out exactly where that's at. It looks like it's around like 5 or something, right? Okay, so let me turn the lights on. Let's see if we can just ignore that. Okay, so we'll go over, we'll just do the math in between here. So should I take the derivative straight out? Just take the derivative of A? You could. But what'd you have to use?
The quotient and product.
Product rule and the... Oh, that'd be ugly. You could at least like rewrite that as 24x to the -1, but ugh, that doesn't sound very fun. Let's distribute. So this is going to be 24, and then we've got 72 over x. It's 24 times 3, 72?
Yeah.
And then we've got 2x, and then we've got 6. So we can put those together, and we can say our function is going to be 2x plus 30 plus 72 over x. Now to find that minimum that we're looking for, we're going to take its derivative. So 2. And we said, what should we rewrite that 72 over x as? So we don't have to use the quotient rule.
For 72, x to the 1.
So that's going to be -1 times 72 x to the -2. So that's 2 minus 72 over x squared. And then we want to set it to 0 to actually find our critical points, right? So we say set it to 0. What should I probably do with those things if I want to set that to 0?
Oh, put a common denominator. So it's
Common denominator, right?
2x squared minus 72.
So one critical point, of course, from the bottom where it's undefined is going to be 0. But is that going to be like the answer to our application here?
Always.
That wouldn't make sense, right? Like then you'd have like a 0-dimension paper, so that doesn't make sense. So we're interested in the ones to the top. So if we do that, we probably won't even need much of a calculator. So we'll say x squared equals 72 over 2. What's half of 72? Is it 36? Ah, no calculator needed.
X equals 6.
Plus or minus 6. So there's technically 3 critical points in this problem, right? 0 from the bottom, and plus or minus 6 from the top.
You can have negative paper.
Well, we don't want negative paper. Does that make sense? So obviously our dimensions that will minimize the amount of paper used is going to be 6 by 6 by what? 6 by 4. Where's the 4 coming from?
The 24.
Money, paper. Oh, that's.
Coming from there, right?
Uh-huh.
So 6 by 4, how's that relate to like a piece of paper that we're used to? So 6 by 4 inches doesn't sound right, but we've got, it's really going to be 6 plus 3 is 9, and 4 plus 2 is 6, 9 by 6. That sounds more like a piece of paper that we're used to, right? 8.5 by 11, something like that. So maybe we should all go to 9 by 6 pieces of paper. Anyway, this is optimization. This is good stuff. This is how everything that's ever like chosen to actually market for people to buy in business and stuff, it's all optimized beforehand.
So
If the company's hoping to make money anyway and not go out of business.
Oh, so you took the 24 equals x, y, because that was then you plugged it in.
Yeah.
So
The key, you can use think of this as like your key, right? Over here in your key you have the original primary equation, and then you might have a secondary equation, and you can always refer back to that key when you're done with your problem to see if you're really done. You know what I'm saying? I always like to keep that information in kind of one area on my paper, maybe even put a box around it. It has all the specific stuff I know about my situation. Okay, let's do one more. One more, and then we'll do 1 or 2 more Thursday. So what do you guys want to do? Do you want to do an intense one?
Yes.
Or would you rather do like one that's similar to these two? Should we wait till Thursday for the intense one, or
Let's do number 64.
Let's do.
who wants
it's
who
pretty
wants
intense.
a more fun one?
Will the intense
I want
one?
a
Will the
fun
intense
one.
one screw us up?
We're gonna do it Thursday, otherwise it's pretty cool.
I want the fun one.
Well, what's Thursday?
Let's do it. Let's do.
Which one are we doing?
We're gonna do the fun. I spent a lot of time making this program last year.
By fun, do you mean?
I didn't say this. It's like,
You say go?
No, it was actually it was actually really nice. It was actually kind of really nice at the same time.
it was,
What was it, Bernie?
It was kind of mean and nice
No,
at the same time.
don't say it.
No, it was I'm not gonna say it. It was
okay, so it was a mean and nice.
I could have
Did I say Archimedes?
It went both ways.
It wasn't like that at all.
Okay.
It not like-
Last one. Okay. So this problem says, find the dimensions of the cone. So we got a cone trapped inside of a sphere. It has to stay. It has to like. No, I don't think so. It has to stay on the edges. You guys know what I'm saying? It has to be inscribed in geometrical terms. So you got a cone inside of a square, inside of a sphere. And the problem says, find the dimensions of the cone of maximum volume that can be inscribed in a sphere where the sphere is like stuck at a fixed radius. You guys know what I'm saying? So we're supposed to maximize how much we can put in that cone.
Is it a cylinder that you can fit three?
You can do this with a cylinder too. I think maybe you probably think that. So let's imagine what's happening. Here's the cone. It's sliding along. Well,
This is awesome software.
it's supposed to slide along. It's supposed to slide along smoothly. Anyway, so think about the volume of the cone as we go here. Where do you guys think the volume of this cone is going to be the most?
Like right.
Is it going to be like way down here, where it's a thin
No.
cone? When? Getting
No.
more, right?
When it's when it's like
There.
half,
Like right there.
There.
not too fast.
See how I have it built up so you can see how much volume it actually has over there off to the side? So like, would it be all the way up here?
No.
No.
About right.
Isn't it a little bit more, like right about...
There.
You want to get a
Nope.
Oh,
Nope.
oh.
Nope.
33 degrees.
Yes,
Right.
yeah.
Oh,
it's
One
not-
more.
A little
One
bit
more.
more.
One more.
A little bit more.
One more. You can get to 9.5. You can do it.
Nope.
Up, 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 up.
No.
Success. So, remember, our question was, what are the dimensions of that cone? Okay, so what are the dimensions of that cone? So we need to talk about in terms of a radius. So I'm going to turn off the projector and we're going to finish this. Oh, Jake, can you just hit it? Yeah. Thank you. Okay, so maybe we just need a primary equation this time. Maybe we need to pull in another one. Let's see what happens. So I'm going to draw our situation as best I can. So there's our sphere. I think a key to this problem is that you remember the sphere. Was the sphere changing?
No.
It was fixed, right? Like it stayed the same size. The cone is the thing that's changing and it's variable. So let's keep that in mind. And I'll try to draw the cone. We said it looked like it was going to happen about right here, right? Something like that. Okay? So, what are we trying to maximize again?
Cone
The
size.
volume of the cone.
The volume of the cone. So what's our primary equation?
The volume of the cone.
Volume of a cone.
Isn't it 1/3?
1/3.
Pi.
Close. That's like a sphere. A sphere is 4/3 pi r cubed.
What about
Cone is 1/3 pi r squared and also
height?
h. Remember, this is a cylinder right there. That's the volume of a cylinder. If you put the 1/3 in front, that cuts out like the extra parts from the cylinder. Okay? Anyway, so there's the volume of a cone. That's what we need to take the derivative of. But once again, how many variables does it have in it?
3, no, 2.
That's a function of r and h right now.
But it said R was fixed.
It said something about something being fixed, so that's what we need for our secondary equation.
No, the R is going to change. The R of the
So-
cone won't,
so-
the R of the sphere won't change. The R of the
Yeah.
cone will change.
Okay, so somehow we need to relate the r of the sphere to the r of the cone. Can we do that maybe somehow? Can we like look at this?
It will always be less than.
Yeah,
So what is this dimension right here?
that's the height.
That's the height of the cone. Okay. Let's look at that. What else do we know? So this little r is the r of the cone, right? The big R is the r of the sphere. So, we maybe go out from a point right here. This would be a clever choice. Where am I going to take this?
Anywhere, it doesn't matter, does it? Oh, you mean a triangle, okay.
Yeah. If it touches the edge anywhere, and I'm considering this as, what am I thinking of this point is, really? It's the center, right? The center of the sphere. If I draw it out to the edge anywhere, it's the radius of the sphere, isn't
Right.
it? So let's call that big R. That's the thing that's fixed. So maybe it's 10, maybe, I don't know what it is. We're going to call it big R. Okay? So now, think about this triangle. If you could somehow get the sides of that triangle, I think it's going to do what we know. So we know that the hypotenuse of the triangle is big R, right? What's this little thing? Don't think too hard.
Just
Pythagoras.
R. It's just R.
Yeah, we're going to use Pythagoras to get our secondary equation, but we need these sides first.
It's just R.
It's just little r. Why did Brenda say that's little r?
It's because
That's
it's
the radius of
the
the
radius
cone.
of the cone.
That's the radius of the cone. Nothing sneaky is going on here. The only part that's hard is this. What is this distance?
H minus big R.
Okay, you guys hear Paul? Paul said this part from here to here is h minus big R. Do we all see why that's true? Because this distance was h, and this part is how much? Isn't that another big R? Because it's from the center out to the edge. This is also big R, so h minus big R, whatever's left is that thing right there. Then we're going to apply Pythagoras, and we have our secondary equation, which we can stick into that. So it was tough to get the secondary equation in this, but that's the only hard part of this problem, I think. So let's see. Pythagoras says that little r squared plus, maybe I'll put this over in my key. I like to keep those together. So little r squared plus h minus big R squared equals big R squared. Now, what did we really want to do again? We really wanted to get rid of one of these. You could do it either way, but let's see, which one did I get rid of in case we get lost? I solved for little r. That'd be pretty easy to do, right? If you want to solve for little r. Little r squared is big R squared minus this. So little r is square root of that.
Let's look at the distance.
It looks ugly, but
Let's look at distance.
keep your
before we
focus.
go.
It does kind of. It's the distance formula in spherical coordinates. Anyway, so we're going to plug that in here. So we've got 1/3 in pi. That's just a constant, so in calculus land it's easy, right? Anything constant is easy. And then we say, okay, Should I put that square root in there or not?
No, not if it's square.
It's really just r squared, so you could look there, or you could think squaring the square root gets rid of it, right? So we've got that thing, and then we've still got an h. So this is a function of what now?
Of R.
Big
Of H.
R.
Only of h. What you've got to keep in your mind, and you probably want to put it somewhere, is that why is that not a function of big R2?
Because R is
Constant.
constant.
R is constant. If you want, think about it as 10. Just so you can be thinking about it as constant, okay? So all we've got to do now is take a derivative, and you're saying, oh my gosh, that thing looks like the most terrible thing ever to differentiate. But all kinds of things in there are just constant. It's easy. It's like a polynomial. You know what I'm saying? It's like x squared something. So just distribute and see what happens. So let's see. First I'm going to distribute before I take the derivative. So let's see. This and this and this is going to be 1/3 pi big R squared h. Yeah? And then let's just put all these in front of that. So then we're going to have minus 1/3 pi h minus r squared. Take the derivative of this, it's just that number, right? Because h is the variable. That's why you need to be writing these like this. What are they functions of? So you know which things are variables and which things are fixed. And you just don't have to worry about them, okay? If we took the derivative here, what would we have to use right now?
Chain rule.
Yeah, chain rule, but the product rule. Ugh, so do you want to do that or? I don't. What should we really do with this part?
Expand.
Expand it. So what is that? Instead of being h minus r, it's going
H
to be
squared minus RH.
2rh
Plus R, big R squared.
plus big R squared, right?
Oh, I see what you're saying.
Okay. So then we're going to say, it looks ugly, but if you keep in mind that r is constant and pi is constant, this isn't going to be that bad. So then we're going to distribute this to each one of those. So that's minus 1/3 pi h to the third, and then this one's going to be plus 2/3 pi r h squared, right? And then this one's going to be minus 1/3 pi h r squared. Now before we take a derivative, do any of those cancel? Let's just see. Does anything cancel here? Or can we put it together? Any like terms?
Those first and
First
third one?
and last.
First one is r squared
no.
h.
H squared.
The
So
H is
first and or second.
R squared h in both, right?
They're both the same.
And they're exactly the same.
So you just cancel.
Those just go away, don't they?
Yeah.
Yay. These go together.
Yay.
You can pull.
You can factor some stuff out, but
Then you just
that would make the derivative messier. Yeah. So let's take the derivative of that. So finally, we're taking the derivative. So the derivative is going to be what? What's going to happen with this 3 and that 3?
Ooh, cancel.
So you have negative pi h squared, and then derivative of this. Remember, that whole thing in front, those are all constants. So it's really just the derivative of h squared, which is what? 2h. So we're going to have 4/3 pi r h. There's the derivative. Watch how elegant this is going to be that it comes out. It's such a cool problem. So now, okay, we've got the derivative. What's the next step in our process? We find the,
set it to 0.
set it to 0, we find the critical points. It's just a polynomial, so we say 0 equals that stuff. And now, can we factor?
H.
Remember, once again, just keep telling yourself this. Pi is constant and big R is constant. Just numbers.
A pi
Pull out
H.
pi h.
We can pull out pi h. Okay. So if we pull out pi h, we've got a negative h left there. And we've got plus 4/3 pi r there.
No
No,
pi.
pull the R.
Oh, we pulled out
Pi,
the,
pi.
we pulled out the pi. Okay. All right. So h equals 0, is that going to be a very interesting scenario? That's not going to be anything. So the one that's going to be interesting is when this thing equals 0. Remember, variable here, once again, you can't say it enough times, is h. So I'm going to move that over to the other side. So
It
H,
It's, oh, never mind.
now there's our answer. So let's interpret what that answer means. Does that make sense with the picture that we have drawn right now when we kind of visualized it in the software? We said it'd be about right there. When H is 4/3 R, well R is like this, so 4/3 of R would be like about that much, wouldn't it? Well, what the question really asked, the question said, find the dimensions of the cone of maximum volume. It didn't say what that volume was, it said find the dimensions. So one of the dimensions is its height has to be 4/3 of what?
The radius of the radius of the sphere.
The radius of the sphere. So this is one we really need to write out. So the cone of max volume, I'm going to say trapped in a sphere of radius r happens when its dimensions are h equals 4/3 of that radius, and its radius is going to be then what? We'd have to go back up here and plug in. So I trust that you guys could get that. Oh, I didn't even do it, so you'd have to plug back up in there, yeah. So you put h equals 4/3 of r, and you can figure out how big that little radius would be. Does that make sense? So that's the kind of language I would like to see you guys using. So that shows you really understand what's happening. It's necessary. Hope you found that was cool. That's what we visualized, right? It was a little bit more than 4/3 of the big radius. It was like, it was about that far.